Okay, this is chapter 5.2, properties of rational exponents and radicals. So the essential question here is, how can you use properties of exponents to simplify products and quotients of radicals? What you will learn is how to use properties of rational exponents to simplify expressions with rational exponents. And we're going to use properties of radicals to simplify and write radical expressions in their simplest form. Okay, properties of rational exponents. The properties of integer exponents that you have previously learned can also be applied to rational exponents. Hopefully you remember all those. Core concept, properties of rational exponents. Let a and b be real numbers, and let m and n be rational numbers. Okay, so a rational number is anything that can be represented as a fraction, like a over b. Rational. Real numbers can be rational, they can be irrational, but they're all real as long as they're not imaginary, which is the square root of -1 factors, such that the quantities in each properties are real. Okay, so we're going to take real numbers, and m and n are rational numbers, and their quantities in each property will become real. So product power, just a quick review. A to the power of n times a to the power of n equals a to the power of m plus n. You add the exponents. So 5 to the 1/2 times 5 to the 3/2 would be 5 to the 1/2 plus 3/2, which is 4/2, or 2 and 5 squared is 25. The power of powers rule says to multiply. Power of a to the m to the power of n is a to the m times n. So if we had 3 to the 5/2 and then we square it, it's 3 to the 5/2 times 2, or 3 to the 5th again, and that's 243. Power of a product, a to the a times b quantity to the power of m. You distribute the m to both components, so it's a to the m, b to the m. So if I have 16 times 9 to the 1/2, it'd be 16 to the 1/2 times 9 to the 1/2, and 1/2 means square root, so square root of 16 is 4, square root of 9 is 3, 4 times 3 is 12. Negative exponents, a to the negative m. The first thing we do is take its reciprocal to make m positive, 1 over a to the m. But when we do that, a cannot equal 0, because then we have an undefined value, and that is not real. 36 to the negative 1/2, therefore would be 1 divided by 36 to the positive 1/2. That means square root of 36, so that's 1 over 6. A 0 exponent, a to the 0 equals 1, where a is not 0. So 213 to the 0 power equals 1. And I'm going to stop and explain that further, because most books don't. Why is a to the 0 equal to 1? That's the big question. Okay, and it comes from the power of quotients, or actually the quotient of powers rule right down here. So I'm going to get back to that in a second. So we have a to the m divided by a to the n. We get a to the m minus n, where a cannot be 0, or this would be undefined. So 4 to the 5/2 over 4 to the 1/2 is 4 to the 5/2 minus 1/2, which is 4 to the 4/2, or 4 squared, which is 16. Now I'm going to talk about a to the 0 equaling 1. If I have a to the m over a to the n, and the rule says that we take a to the m minus n, well, if m and n are equal, let's say a is 4 and m is 3, divided by 4 and n is 3, then we would have a to the m, a to the m minus n. 3 minus 3, you subtract the powers. Well, that's obviously 4 to the 0, and 4 times 4 is 16, times 4 is 64. Well, this would be 64 over 64 if I went the other way. If 4 cubed over 4 cubed, anything divided by itself is, drum roll, 1. And that is why something to the power of 0 is 1. Now the power of a quotient, a over b to the power of m, is equivalent to a to the m, b to the m. So in other words, we're doing the same thing as we did up here as power of product, and the power gets distributed to the numerator and the denominator. So if we have 27 over 64 all to the 1/3 outside, we distribute that 1/3 to both the numerator and the denominator, and that comes out to be 3/4. That's the cubed root of 27 divided by the cubed root of 64. and we get 3/4. So there is a quick review of the core concepts for the next problems that we're going to do. Okay, example 1, using properties of exponents. Use the properties of rational exponents to simplify each expression. So we have 7 to the 1/4 times 7 to the 1/2. Now, let me go back and point something out to you. Notice how these are all A's. And here's an A times B. But when we have these rules, our bases, the base A has to be the same. So going back to here, 7 and 7 is the same base, so I can do these rules. If this was 7 and this was 3, I can't apply the rules because the bases are not equal. We have two different values, A and B. But if they're equal, like 7, then we can take the rule. And when multiplying exponents, we add the exponents. So you take the same base, 7 to the 1/4 times 7 to the 1/2 is 7 to the 1/4 plus 1/2. Well, 7 to the 1/4 plus 1/2 is 7 to the 3/4. Okay. And we could probably go a little bit further than that. So that's going to equal, think of that as the 4th root of 7 cubed. That's what it means. So if I get my calculator out, those numbers can get fairly large fairly quickly. If I take 7 to the 3rd power, that is 343. And then if I take the 4th root of 343, do I get a rational number is the question. So I want to take the 4th root of, so there's a 4th root of 343, and I got 4.303, so it's irrational. So we could just leave it as 7 to the 3/4, or it is the cubed root of 7. 7 cubed, I mean, 4th root of 7 cubed. There it is, the 4th root of 7 cubed. All right, next one, 6 to the 1/2 times 4 to the 1/3, all to the 1/2. So 6 and 4 are not the same base. So I can't just take 1/2 and add 1/3. So that I cannot do because these are not the same. But I can take and distribute this 2 outside to both. So it's 6 to the 1/2 squared times 4 to the 1/3 squared. And then when I simplify that, 1/2 times 2 is just simply 1. Okay, 6 to the 1/2 times 2 times 4 to the 1/3 times 2. Well, 1/2 times 2 is 1, so it just gives us 6 to the 1. And 4 to the 1/3 times 2 is 4 to the 2/3. And that is going to equal 6 times 4 to the 2/3, because we just don't show that 1. And we're just going to leave it at that. I can't say that that is 24 to the 2/3. Be very careful. So let me revisit this. If we have order of operations, which is called PEMDAS, parentheses, exponent, multiply, divide, add, and subtract. If I'm going to simplify this radical, the first thing you have to do is exponents. You can't multiply 6 and 4 because multiplication comes after. So the order of operations would say to do this first. So do not say 6 times 4 to the 2/3 is 24 to the 2/3. It is not. It's 4 to the 2/3, and whatever that is comes out to be 6. Or whatever that comes out to be, you multiply by 6, I mean. Okay, so we'll just leave it at this for now. Now we have 4 and we have a 3. The bases are not the same. There's nothing I can do inside this parentheses at the moment, but it's to the power of -1/5. So the first thing I want to do is flip everything that's in the parentheses will become my denominator, and the 1 on top, and then the 1/5 will become positive. So you take 4 times 3 to the 5th. Okay, so then they're just putting brackets around the whole thing to the -1/5. Okay. So what they're doing here now is they factored out the 5 since the power is the same in both. So we can say it's 4 times 3. With the same power, you can pull that out and factor out the exponent, if you will. And then that would become 12 to the 5th to the -1/5. Okay, 4 times 3 is 12. And they're both to the 5th, so we can do that. And then 5 to the power of -1/5, you multiply. So it'd be 12 times to the power of 5 times -1/5. And that's going to become -1. So in order to finish this, we just have to take the reciprocal, which is 1/12. Okay. That one we could do a couple of different ways. I could have put a 1 over it first, like I was saying, and make that a positive 1/5 and then work it out. We would have ended up with the same here. The 1 would never have changed, and that would have become 12 down below as well. Okay, so now we have 5 over 5 to the 1/3 equals 5 to the 1 divided by 5 to the 1/3. Okay, so all we did in this step here was put a 1 where you don't see anything. Now the rule says when you have the bases that are the same and you're dividing, you subtract your exponents. So it's 5 to the 1 minus 1/3. Well, that's 5 to the 2/3. And that's it, we're done. E is 42 1/3 over 6 1/3, and it's all squared. So the first thing I can do is I can pull out that power that's the same. So this is very similar to this problem right here. So since the bases were different, but the powers were the same, you can pull the power outside, and it's actually like factoring out the exponent, if you will. So we're going to do the same here. We have a 42 over 6, and they're both to the 1/3, so I can factor out that exponent and say 42 over 6 to the power of 1/3. In parentheses, the 1/3 comes outside the parentheses, and then the 2 is outside the brackets. Okay, and then order of operations says to do what's inside the parentheses first. Well, 42 divided by 6 is 7 to the 1/3 squared. Now I can do my power rule, which is up here. So sometimes there's multiple things we have to do to get this simplified. So 7 to the 1/3 to the power of 2 is 7 to the 1/3 times 2. And then 7 to the 1/3 times 2 is 7 to the 2/3. And we could rewrite that as well, but we don't have to. It says use properties to simplify each expression. This is also equivalent to the cube root of 7 squared, which would be the cube root of 49, but that is irrational. 49 is not a perfect cube. So that's it. 7 to the 2/3 would be the best way to leave that simplified. Okay, so with all these rules reviewed on the properties of exponents, you should now be able to do numbers 3 and 4. All right, simplifying radical expressions. The power of a product and power of a quotient properties can be expressed using radical notation when m equals 1 over n for some integer n greater than 1. Okay, so because if n was less than 1, let's look at it this way. If n was less than 1, like a half, 1 divided by 1/2 is the same as 1 times 2 over 1, which is 2. Okay, so we don't want anything less than 1. And if n is 0, it's undefined. So n has to be greater than 1 for these to be useful. So the properties of radicals, it says let a and b be real numbers, and let n be an integer greater than 1. Integer. In other words, 1, 2, 3, 4, 5, 6, out to infinity. No fractions, no decimals. That's what an integer is. Okay, and it's an integer greater than 1. So 2 or greater. Property name, product property. Okay, so remember n has to be 2 or greater, and it's got to be an integer. We don't take fractional radicals in this course. So a times b, that they're real numbers, there's no imaginaries. A times b underneath a radical to the nth degree, or nth power, the nth root of a times b, there it is, equals the nth root of a times the nth root of b. In other words, what we can do is we can split this thing up into 2 and give them the same index. That's what it's called out there. This is called the index. So let's start with that. Index. That's the radical. This is the radicand. Okay, the radical. So there are the terms for a square root symbol or a root symbol of any degree. The number out here is the index. The number underneath is called a radicand, and the radical sign is just called a radical. So this says the nth root of a times b equals the nth root of a times the nth root of b. So if we had the cubed root of 4 times the cubed root of 2, then that is equal to the cubed root of 4 times 2, which is 8. And the cubed root of 8 is 2. because 2 times 2 times 2 is 8. Now, the quotient property states that if you take the nth root of a fraction, a over b, then that's equal to the nth root of a divided by the nth root of b, where b is not 0, of course, or it's undefined. So if I take the fourth root of 162 and divide it by the fourth root of 2, that's the same as taking the fourth root of 162 divided by 2, and half of 162 is 81, and the fourth root of 81 is 3. Okay, so that is the properties of radicals. Okay, example 2 says using the properties of radicals. Use the properties of radicals to simplify each expression. So I have an index of 3, I have an index of 3, therefore I can combine my radicands by the operation in between. So this is going to equal the cubed root of 12 times 18. So I write it like this: the cubed root of 12 times 18 underneath, and 12 times 18 is 216. So it's a cubed root of 216. Well, the cubed root of 216, how do I find that? How do I simplify a cube? You go like this. This ends in 6. It's an even number. So you take the smallest prime number on the left, and so half of 216 is 108. Now I do it again. It's still even, so I'm going to put a 2 over here. Half of 108 is 54. Still even, so I'm going to do it again. 2, half of 54 is 27. Now it's odd, but it's a factor of 3. So 3 times 9 is 27, and 3 times 3 is 9. The index is 3, which means I need 3 of each number to become 1 outside. So think of this as 2 on the outside of the cubed root, and the cubed root of 3 times 3 times 3, which is 27. The cubed root of 27 is 3, and the cubed root of 8, which 27 times 8 would give you 216, is 2. So I have a 2 and I have a 3, so that would be 2 times 3, or 6. Okay, so that is 6. Okie dokie. All right, so let me erase this. Next one. Fourth root of 80 divided by the fourth root of 5. Our indices, our indexes are 4, so they're the same. So now I can make a big radical with a 4 on the outside still, and my fraction goes underneath one radical. So it looks like this. So it's a fourth root of 80 divided by 5. 5 goes into 8 once with a remainder of 3. 5 goes into 36 times, so it's 16. So this is the fourth root of 16. Now again, we come over here and we take 16 and it's even, so it's 2 times 8. 8 is even, that's 2 times 4. 4 is even, that's 2 times 2. And lo and behold, we get 4 2's. Our index is 4. So we need 4 2's to become 1 2 outside. So the fourth root of 16 is 2. And that's all there is to it. So now an expression involving a radical with index n. N is in simplest form when these three conditions are met. 1, no radicands have perfect nth powers as factors other than 1. 2, no radicands contain fractions. So what they mean by step 1 is, let's use the first one as an example. This is the cubed root of 12 is what I'm talking about. So if I take the cubed root of 12, this says no radicals have perfect nth powers as factors other than 1. Okay, so in other words, 12 is 2 times 6, and 12 is 2 times 3, and 3 times 2 times 2, I don't have 3 2's, so therefore I can't simplify that. That's what this means. So I cannot simplify the cubed root of 12. It only has factors of 12 and 1. No radicands have perfect nth powers as factors other than 1. So there are no factors I can take out is what it means. No radicands contain fractions. And no radicals appear in the denominator of a fraction. Okay, So in other words, if I ended up with this 1 over, I don't know, the square root of 4, I cannot, I actually don't want 4 because that's just 2. If I had 1 over the square root of 5, I cannot simplify that square root. And I can't have a radical in the denominator. So what I would do is multiply the top and bottom by the square root of 5, because anything divided by itself is 1. When I multiply this times 1, this is 1, it stays the same. Well, 1 times the square root of 5 over the square root of 5 times the square root of 5 is 5. So if I go to my calculator and clear it, and I say 1 divided by the square root of 5, I got a decimal, 0.4472135,955. If I take the square root of 5 and divide it by 5, whoops, I forgot to get out of my radical first. So square root of 5 divided by 5 is that same value. So 1 over root 5 is equal to the square root of 5 over 5. And that proves it right there. Okay, so do not leave answers with a radical in the denominator. To meet the last two conditions, rationalize the denominator, that's what it's called, by multiplying the expression by an appropriate form of 1, root 5 over root 5. That eliminates the radical from the denominator. So that's what I just showed you. All righty. Okay. Example 3, writing radicals in simplest form. Write each expression in simplest form. The book shows one way to do it, but they were asking you to try to find perfect cube factors of 135 to come up with 27 times 5. I prefer not to do that, so I'm just going to show you how to do it with a factor tree. So I'm going to take 135 and do a factor tree. And 5 plus 3 is 8 plus 1 is 9. And there's a rule why I do that. If the sum of the digits is divisible by 3, so is the number itself. And 5 plus 3 is 8 plus 1 is 9. That's a multiple of 3. So therefore 3 will work. 3 goes into 13 4 times. That's 12. The remainder of 1. 3 goes into 15 5 times. 5 plus 4 is 9. 3 goes into 9, so 3 goes into 45. 3 goes into 4 once. Remainder of 1. 3 goes into 15 5 times. 5 plus 1 is 6. 3 will go into 6. 3 goes into 15 5 times. So I get 3 3s. And our index is 3. So 3 3s become 1 3 outside. The 5 left over stays as a cubed root of 5. So that's how you do simplification of a cube using a factor tree. So it's 3 cubed root of 5. And if you're ever wondering if your answer is right or wrong, you can always check. So I want the cubed root of, let me clear my screen. So what are we doing here? We're doing the cubed root, whoops, what's going on here? We're doing the cubed root of 135. Let me put this back. So I do math, cubed root is 4, and then 135, and I hit enter. And I got 5.12, and I got 3 times the cubed root of 5. So now I'm going to put that in. 3 times math, 4 for cube root, and I put 5 in the radical, and I hit enter. 5.1299278.4. They match. So that confirms that this cubed root of 135 is equal to 3 times the cubed root of 5. All right, B is a little different. B has a radical in the denominator. They're both fifth roots. So really this could have started out like this. The fifth root of the whole fraction 7/8. And then we simplify it by breaking up the numerator and denominator, but they did that for us already. And then we want to factor this further because we can't have a radical in the denominator. So if I go back to my rule, it says to meet the last two conditions, no radicals in the denominator, you have to rationalize the denominator by multiplying the expression by an appropriate form of 1 that eliminates the radical form in the denominator. So I could multiply this by the fifth root of 8, but then we'll have to do some simplifying. So what you really want to do is not times the fifth root of 8, because that's only times 2. When it's a square root, you can just do another one. What you want to find is something that will give you a perfect cube. So 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27, and so on and so on and so on. Actually, not by, why am I doing threes? I'm doing a fifth root. My apologies. A fifth root. Oh, so that's 1 times 1 times 1 times 1 times 1, and that is 1. 2 times 2 is 4 times 2 is 8 times 2 is 16 times 2 is 32. So there is a fifth root. Our smallest fifth root other than 1 is 32. And then you have to ask yourself, does 8 go into 32? And it does. 8 times 4 is 32. So I'm going to take the fifth root of 4 over the fifth root of 4. And that is going to give me the fifth root of 7 times 4 over the fifth root of 8 times 4, if you will. Okay? And that's going to simplify to the fifth root of 28 over the fifth root of 8 times 4, which is 32. Well, the fifth root of 32 is 2. So this is going to simplify to the fifth root of 28 over 2. And that is our answer. So this one's a little trickier. You can't just take the fifth root of 8 times the fifth root of 8. You can only do that with squares. Multiply it by itself to get rid of the square. But when there's 5 of them, you'd have to multiply it 5 times, and you need to find a number that will do that. That'll give you a multiple of what's in the radical. Okay, so hopefully you get that. If not, rewind, play again, and then you should be able to do problems 21 and 22. Okay, one more thing we can run into, and those are conjugates. So it says for a denominator, that is a sum or difference involving square roots, multiply both the numerator and the denominator by the conjugate of the denominator. The expressions a square root b plus c square root d and a square root b minus c square root d are conjugates of each other, where a, b, c, and d are rational numbers. So the conjugate of something is just taking the first term, which it never changes, and the second term that doesn't change, but the signs do. So it's just the opposite sign in between, and that creates a conjugate. So here is a radical. It says write it in simplest form. So 1 over 5 plus the square root of 3. Okay, and I'm going to write it in simplest form. I don't want a radical in the denominator, so I'm going to multiply by the conjugate. Well, the conjugate of 5 plus the square root of 3 is 5 minus the square root of 3. The only thing that changes is the sign in between. And you put that in the numerator as well, because anything divided by itself is 1. So this times 1 does not change its value. So 1 times 5 minus root 3 is 5 minus the square root of 3. And here's where you need to be careful. We're going to FOIL. So I'll do this off to the side. 5 plus the square root of 3. Now I'm going to put it in parentheses so it looks like two binomials that we FOIL. First is 5 times 5, which is 25. Outer is minus 5 times 3, root 3. Inner is positive 5 times the square root of 3. And those two values are going to cancel. That's 0. And then plus times a negative is minus. And the square root of 3 times the square root of 3 is 3. So this is 0. So 25 minus 0 is 25. Minus 3 is 22. So this is 22. So we have 5 minus the square root of 3 over 22. So radical expressions with the same index and radicand are like radicals. To add or subtract like radicals, you use the distributive property. All right, little note after the fact. So this is the radical simplified. Cannot have a radical in the denominator. It is not simplified. This is. Now you should be able to do numbers 29 and 30. Okay, so as I said in the last page, I read it, but here it is. Radical expressions with the same index. Here's a 4, here's a 4. And radicand Here's a radical 10, here's a 10, radicand 10 and 10. They're the same, are like radicals. To add or subtract like radicals, use the distributive property. So the easiest way to explain this is if I have the fourth root of 10 and I think that is x, and this is the fourth root of 10 and that's an x, then I have x plus 7x. Think of that as 1x. 1x plus 7x is 8x. Okay, but in our case, x is the fourth root of 10. So then if I just erase that here and replace that with the fourth root of 10, my answer is 8 times the fourth root of 10. Of course, we're not going to do that every time with an x, but you get the idea. It's the same rules as if that were an exponent. So the first thing you want to do is remember that there's a 1 in front of that. So it's 1 times fourth root of 10 plus 7 times the fourth root of 10. So it's 1 plus 7, and I'll put that in parentheses, times the fourth root of 10. And then that's 8 times the fourth root of 10. That's how you would do it right there. So here we have 8 to the 1/5, 8 to the 1/5. They are the same, so I'm going to take 2 plus 10 times 8 to the 1/5. 2 plus 10 is 12 times 8 to the 1/5. And that's it, we're done. 12 times 8 to the 1/5. All right, now this one, I do not have a radical 2 and a radical 2, so I need to simplify this to get down to a radical 2. So I'm taking the cube root of 54, and I'm going to do a factor tree. And 5 plus 4 is 9, so it's divisible by 3. And 3 goes into 5 once with a remainder of 2, and 3 goes into 24 8 times. 8 plus 1 is 9, 3 will go into that. 3 times 6 is 18. And 6 is a factor of 3, and it's even. So that's, actually, let me put the 3 on the left. That is 3 times 2. The reason I put the 3 first is because the 3's all line up, and there are 3 3's, and my index is 3. So this cubed root of 54 is 3 times the cubed root of what is left over, which is my 2. Now my cubed root of 2 minus my cubed root of 2. Now I have a cubed root of 2 and a cubed root of 2, so I have like radicals. Remember, there's a 1 here. So this would be 3 minus 1 times the cubed root of 2. And 3 minus 1 is 2, cube root of 2. If you ever wonder if you're doing it right, you can always use your calculator. That's why I like using a Texas Instruments calculator. I can put this in my calculator and get a value and see if it matches my answer. So I'm going to do that on this case. All right, so it's cube root. So that's math. Cube root is 4, so 4. So there's the cube root of 54. Get out of the radical, minus math 4, the cube root of 2. And I hit enter, and I got an answer to be 2.5198421. So it's approximation, about 2.5. So what is 2 cube root of 2? So I go 2, math, cube root, 2, enter, and I should get the same decimal, and I do. So this is the correct simplification. Okay, so that's simplifying radicals when you have like radicals, and if you don't have like radicals, simplify to see if you can find one so you can simplify everything. Now you should be able to do numbers 37 and 38. Okay, so example 6 says to simplifying variable expressions. Simplify each expression. Okay, I don't do it the way the book does it. I've been doing this a long time, and I see the struggles that students have with trying to follow certain ways. So I've tried to find the best way to explain it. And with the experience I've had, this is the best way to do it, I think. So if I break this up into 2 pieces, I can say the cube root of 64 times the cube root of y to the 6. Okay, I broke it up, and then I'm going to take this 64, and I'm going to divide it by 2. Half of 64 is 32. Half of 32 is 16. Half of 2 is 8. Half of 2 is 4. And half of 4 is 2. I have a radicand, or an index, of 3. So I need 3 2's. and I need 3 2's. So this is 2, and this is 2. And 2 times 2 is 4. So the cubed root of 64 is 4. Okay, so the cubed root of 64 is 4. So we're partly done. Now we just have to focus on y to the 6. Now remember, we need 3 of something, like I showed you in this factor tree, to become 1 outside. So the cubed root of y to the 6 is y times y times y times y times y times y. Y to the 6 just means y times itself 6 times. Well, I have 3 y's right here, which would become 1 y outside. I have 3 y's here that would become another y outside, and y times y is y squared. So my answer is 4y squared. So again, recapping, factor tree for the numerical portion. And then the other thing we can do also, by the way, this is called the power, and this is called the index. That is equal to the power divided by the index if you wanted to do radicals and convert them into rational expressions, rational exponents. And obviously y to the 6 divided by 3 is also y squared. So either way you look at it, I just wanted to show you this is where it comes from, but you can actually just do y to the 6 divided by 3 is 2. So the answer to this question is 4y squared. That is the simplified version of this. How do I check that in the calculator? Well, I'm glad you asked. So let's take a look. That can be done. So how can that be done? Well, we have a y. We can choose any value for y. Let's choose something that's not 1, of course, because anything times 1 doesn't change. Don't use 0, because anything plus 0 doesn't change. Don't use 2, because it's 2 times 2 is the same as 2 plus 2. Choose a value of 3 or greater. So I'm going to just choose 5 just for kicks. And I'm going to make y equal to 5. How do I do that? I hit the 5. I use this STO button, which means store. And then I'm going to do alpha. And y is this green one over the 1. So there's my y. So I'm going to do 5 store alpha 1 enter. Now the calculator knows that y is 5. So if I put 4 alpha y squared in the calculator, that's what I got here. So that means when y is 5, I get 100. So if I do the cubed root of 64 times y to the 6, I should get the same answer. So I go math 4 for the cubed root, 64 alpha y to the power of 6. Okay, that's my original. I should get 100 again. And there it is, 100. So that is the right answer. So that's a really neat way to check with radicals or with variables using the calculator. Okay, so now let's take a look at the next one. Let me get my work out of the way from this first one. And here we go. So let's use purple this time. All right, so we have the 4th root of x to the 4th over y to the 8th. All right. So the first thing I'm going to do is split that up. So it's going to be the 4th root of x to the 4th. That doesn't look like a 4. Let's fix that. Divided by the 4th root of y to the 8th. All right. So now we have the 4th root of x to the 4th. Well, that is going to become x. Okay, but we have to be careful. When our exponents are even, negative numbers are a possible solution, because negative 2 to the 4th power is 32. 2 times 2 is 4, times 2 is 8, times 2 is 16. No, it's 16. So 2 to the 4th equals 16, and 2 to the negative 4th, negative 4th, no, negative 2 to the 4th power is also positive 16, because a negative times a negative is positive. So that gives me a positive 4. And then if I do it 2 more times, because it's to the 4th power, A negative times a positive, or a negative times a negative is positive. And now I have 4 times 4, which are both positive, and I get 16. So negative 2 to the 4th is 16, and 2 to the 4th is 16. So I can't just simply say it's x. It can't come out to be negative, so it's the absolute value of x. So whenever we have even, we throw in that absolute value. All right, so then we have to do the same for y to the 8th, 4th root. So remember what I said, if you have y to the 8th to the 4th, that's the same as y to the 8 divided by 4, and y to the 8 divided by 4 is y squared. So that is y squared. Now, I don't need to use an absolute value around y squared, and you're probably thinking, well, why not? Get it? Why? Why not? Well, if y was 3, 3 times 3 equals 9. If y was -3, -3 times -3 equals 9. So since this is squared, y does not need an absolute value, because even if y is -3, squaring it will give you a positive. So the absolute value is not necessary. So the answer to this is the absolute value of x divided by y squared. Okay, so example 7 says writing variable expressions in simplest form. Write each expression in simplest form. Assume all variables are positive. Okay, so we're not assuming any negative a, b's, or c's. Okay. Now this may look daunting, but it's actually not bad if you break it up the way I showed you. The way the book does it actually looks pretty confusing. So what I'm going to do is just simply break it up first. So I'm going to do the 5th root of 4 times the 5th root of, oops, why did I do 5 divided by? The 5th root of a to the 8th times the 5th root of b to the 14th. That doesn't look like a 14. Times the 5th root of c to the 5th. Okay, so the 5th root of 4 is, you can't simplify that. So that's going to just stay the 5th root of 4, because 5th root 4 is just 2 times 2, and that's only 2. I need 5. So the smallest 5th root other than 1 is 32. So 5th root of 4 just stays. A to the 8 divided by 5. Well, think of it this way. Think of it as 8 over 5, okay? The power over the index, and that's going to equal 1 3/5. So whenever you have a number, that's how many variables that will come outside, and your remainder would be 3, if that makes sense. So I have 5 a's that becomes this one whole outside. So that's going to be times a, and then the 5th root of a, and my remainder was 3. So it's a cubed times. Now b to the 14 is 14 over the index. So it's the power over the index. 5 times 2 is 10 with a remainder of 4. So I need 2 b's outside. So that's going to be 2b. And then what is left over, the ones that's less than 5, which is 4, I'm going to still have b to the 4th inside. Hopefully this makes sense to you, the way I'm explaining it. And then c to the 5th and the 5 divided by 5 is 1. That is just going to equal c. Okay, so now I focus on my numbers outside. So I have an a, I have a 2b, and I have a c that are not under the radical. So I'm going to write that as a, and the 2 will go first because multiplication is commutative. So it's the number first, 2, and then the variables in alphabetical order. So it'd be 2a, b, c. Okay, what I was going to write at first was a times 2b times c, But rearranging this, you can move the 2 in front and it's 2abc. Okay. And that's the way we're supposed to represent it. Number first, then variables. So it's 2abc. And now this may still seem a little confusing, but it's really easy. It's the fifth root of what's left. So I've got a 4. I've got an a to the 3. And I have a b to the 4th. And there it is. That keeps snapping to the first part of the b or the 4 that I draw. So do that. Pause a second. Okay, 4a cubed b to the 4th is still under the radical. All right, so this is just the way I prefer to do it. Hopefully this explanation was understandable. If not, see me in class if you have me. All right, so now we have b. X over the cubed root of y to the 8th. Let's switch to red this time, and I'm going to rewrite it first. X over the cubed root of y to the 8th. First thing I want to do is simplify the denominator. And I want a perfect cube. So I have 8. I need to increase this number so it's a multiple of 3. Well, 3 times 2 is 6. That's still less than 8. 3 times 3 is 9. There it is. I have 8. I only need one more to make this a perfect cube. So I'm going to multiply by the cubed root of y to the 1, which is just cubed root of y. When I do that, I get x cubed root of y on top, right? X times the cubed root of y is the cubed root of y. And the cubed root of y to the 8th times the cubed root of y is the cubed root of y to the 8 plus 1. I'm showing all my work. Those are the rules. When you're multiplying, same bases, you add the exponents. And this is going to become x to the 3rd, or x to the cube root of x times the cube root of y over the cube root of y to the 9th. Okay, and one last time, x times the cube root of y. And here we have 9, which is a multiple of 3. So I'm going to get 9 divided by 3, which is 3. So it's y cubed with no radical. So it's x cube root y divided by y cubed. Okay. Again, you can check this with your calculator by substituting in a value, storing a value for x, store a value for y, plug this in, check to see what decimal you get or answer, and then plug this in and see if you get the same answer. Okay, so now let's do C. I'll switch to green. So now I'm doing this. So I'm going to rewrite it first. 14x y to the 1/3. Now there's no parentheses, so it's just the y to the 1/3 over 2x to the 3/4 y. No, it's not y, it's z. I didn't look up there. 2x to the 3/4 z to the -6. Okay, they're throwing everything at us right now. First thing I'm going to do is split this up with like terms in every fraction. The book is not doing this, but I prefer to do it this way. I have 2 numbers in front, 14 divided by 2. I'm going to make that its own fraction. Then I have x's, x divided by x to the 3/4. Oh, that's messy. It's hard to write this small with this pen. Oops. So it's x to the 3/4. Okay, times y to the 1/3 over, there's no y in the denominator, so I put a 1, times, there's a z in the denominator, and there's no z in the numerator, so I put a 1. So this is the same fraction expanded out. Let me get rid of, oh, I can't, never mind. Wrote that too quickly, just leave it. So this broken up into like term fractions is this. Now I can focus on one at a time. 14 divided by 2 is 7. And remember, the rule for division is subtracting exponents. So this will be times x to the 1 minus 3/4 times y to the 1/3 minus, oops, no, it's not. There's nothing underneath. My fault. Let's just leave that. Y to the 1/3 over 1. I'm going to leave that as is. Actually, no, I'm not. I'm going to get rid of that fraction because anything divided by 1 is itself. So y to the 1/3 divided by 1 is y to the 1/3 times. Now the rule here is if you have a negative exponent, you take the reciprocal and you make the negative positive. So this is going to be z to the 6 over 1, but I don't need to write the over 1 because it's just simply z to the 6th power. All right, so it's getting more simplified. Nothing I can do with this 7 times x. 1 minus 3/4 is 1/4. Y to the 1/3 z to the 6th. Okay, and we're done. That is the answer. So I think it's easier to split it up and give every variable and constant or coefficient its own fraction and simplify each one at a time. And there you have it. Now you should be able to do problems 57 and 58. Okay, this is a long video, long chapter section. Example 8. Perform each indicated operation. Assume all variables are positive. So the first thing I notice when I'm doing 5 or 8a is y radical, or it's the square root of y and the square root of y, which means I have like radicals. When I have like radicals, I perform the operation of the numbers in front. So this would be 5 plus 6 times the square root of y. 5 plus 6 is 11 square root y. And we're done. That's it. It is as simple as that. But then when I come to this one, the cubed root of 2z to the 5th and the cubed root of 54z squared are not like terms. I cannot just say 12 minus 1, and then there's a z outside here. So there's all kinds of stuff going on here that we need to try to simplify and make them equivalent. So what are we going to do? I can simplify this 54z squared. I have a z to the 5th here. They're both cubed roots, but I need to get them to where they're the same and get something that might come out of the radical so that the radicands are equal. Okay, so I have a 2 here and I have a 54 here. I have a z to the 5th here. I only have z squared here. So if I focus on this, I'm just going to bring down this 12. And I have a cubed root of something here. The 2 is going to stay there. It has to. But z to the 5th to the 3rd power is the same as z to the 5 divided by z cubed, which is, actually, I shouldn't do it that way. Let me rephrase that. It would be z to the 5 divided by 3. Okay, you take the power over the index. Well, I need 3 3s to make one z outside, and I have 5. So that can become a z outside. So this would be z, that would be the 3 of them with a remainder of 2. So then it'd be the cubed root of z squared. So z to the 5th is the same as z times the cubed root of z squared. All right, hopefully that makes sense to you. There are 5 z's here. I took 3 of them out and it became 1 and left 2 behind. All right, so that's the z. So that'd be z squared here, but I can move this 12 a little bit. Oh, they're connected, unfortunately, so I'll erase it. So I can move that 12 away, and now this z gets stuck right here. So 12, what I'm doing is this cubed root of 2z to the 5th is the same as z times the cubed root of 2z squared, because I took 3 z's out and became 1 out in front. Okay, hopefully that makes sense. Okay, so the next thing I'm going to do is focus on the other one. So now it's minus z, and then I have a cubed root of 54 And I want to see if I can simplify that. 5 plus 4 is 9, so 3 will divide by it, or it'll be divisible by 3. 3 goes into 5 once, 3 goes into 24 8 times. 3 times 6 is 18, and 3 times 2 is 6. So I have 3 3s. So that's the same as 3. Remember, our root is cubed, so I need 3 3s to become 1 outside, and that'd be the cube root of 2 remaining. Okay, I'm not even talking about z squared, but that's still there as well. So I'm going to put z squared back in there. So this is going to be z times the cubed root of 2z squared. Okay, and now if you notice, let me go back to my highlighter. This cubed root of 2z squared, cubed root of 2z squared, they are equal. So now I can take 12z minus z and get 11z, and then the similar or the like term just follows along for the ride. So my answer is 11z times the cube root of 2z squared. Okay, unfortunately, I made a mistake there. I forgot this 3 that's sitting here. So my apologies. That's got to be here. Okay, I needed to move that there. I forgot it. So let me erase this 11. And 12 minus 3 is 9. So it's 9z cube root of 2z squared. All right, sorry about that. So those 3 3s that were inside became 1 outside. That goes in front of the z that was already there. Got like terms, and that comes down as 1. Okay, now that's correct. So now you should be able to do problem 65 and 66. Okay, so that brings us to the end of a really lengthy chapter section. 5.2 had 8 examples. So I tried to narrow down the number of problems you had to do by only giving you 2 for each example. So hopefully this is manageable. So here it is. Thanks for watching and have a great day.